All right, we're moving into 16.4. This is one of the major theorems of this course or any other course. It is a generalization of the fundamental theorem of calculus that we get to use when we're doing path integrals. So the name of the theorem is Greens Theorem. First we need a definition. That C be a simple closed curve, SCC, simple closed curve, in the plane, given by R of t on the closed interval AB. That's our setup. A positive orientation of C is a counterclockwise traversal of C. So the region will be on our left. So that looks like this. Here's the plane. Here's my curve C. A counterclockwise traversal means that we're going to go in this direction around the curve. So if I'm walking around there, I have my head sticking out of the board, I'm walking around there, the curve is on my left. Excuse me, the inside of the curve is on my left. All right, here's Greens Theorem. One of the great theorems in mathematics. This is one of those theorems that you really want to remember at the end of the course. Years from now, people say, multivariable calculus, what's that about? You'll say, well, there were partial derivatives, there were double integrals and some triple integrals. Oh, and there was Greens Theorem. That's what I want you to remember. All right, here's Greens Theorem. Let C be a positively oriented, piecewise smooth, simple closed curve. Aren't you glad we got all those terms out of the way already? In the plane. And let D be the region bounded by C. If P and Q have continuous partials on an open region containing C, or D, on an open region containing D, then, here's the magic. Path integral, I'll explain the little circle in a minute, over C of P dx plus Q dy is equal to the double integral over the region D of Q sub x minus P sub y dA. This little circle here is to tell us that C is closed and positively oriented. Okay, it's just a reminder that that's the kind of path integral that we're talking about there. Okay, so what does this theorem say? Well, first of all, this path integral is path integral over C of PQ dot dr. Okay, do you recognize that? So it's one of those kinds of integrals. It's just a path integral. I've written this with that first instead of equal to this double integral. Think of it the other way. I'm computing this double integral of something over this region D. What this theorem says, you notice that these are partials and these are not. right? This is the original P and Q, these are their derivatives. What this says is that if I can find P and Q whose derivatives look like this, then instead of looking at this double integral of whatever this function is, I can look at the boundary of my region and look at this antiderivative kind of thing. Now, in Calc 1, Calc 2, antiderivative was pretty clear, right? It's a function whose derivative is your function, your integrand. Here it's not so clear because I've got these two functions, Q and P and Q, and these two partials that I happen to have chosen here. Not really chosen, they're forced on us. So antiderivative, it's not quite so clear what you mean. I mean, if this is 3x, well, what's P, what's Q, how do I assemble that? But nevertheless, the P and the Q are some kind of antiderivative sort of thing of Q sub x minus P sub y. So what the theorem says is, instead of looking at the integrand, I'm going to look at this antiderivative kind of thing and see what it does on the boundary. And that's exactly what the fundamental theorem of calculus says to do. The difference is that in the fundamental theorem of calculus, the boundary is just 2 points, right? It's the endpoint of the region. It's the endpoints of the region of integration. So let's look at this here. We'll just do this comparison. So I have my region D surrounded by this curve C in the xy plane. I have positive orientation on this. I'm traveling around in that direction. And this theorem says I can find the double integral of my function over that shaded region, or I can find this path integral on the boundary. The fundamental theorem of calculus says if I want to find a path, if I want to find an integral, if I want to find this area, I shouldn't shade it because that makes it look like I'm integrating over that region. Okay, I have both. If I want to find the integral of this function, instead, what I can do is find this antiderivative of it and evaluate it, see what that thing does on the boundary. Right? The boundary is just the 2 points A and B. So here's my antiderivative operating on the boundary in some way. Over here, this funky thing, this P and Q arrangement, is my antiderivative kind of thing, just focused on the boundary. So it's the same kind of principle, although it looks different in 2 dimensions than in 1. So let's try an example. So first thing, I'll tell you now, I'm going to ask you to state Greens theorem on the final exam. I will ask you to state Greens theorem on the final exam. So when I say state Greens theorem, I mean the whole thing, right? You don't need this bottom part here, or the red. But the whole statement of the theorem, including all of the hypotheses, because if you don't have the hypotheses, you don't have the theorem. So this is something you're going to want to memorize. You have lots of time. I'm giving you early warning. There you go. Okay. Let's try an example now. Let's see how this works out. I'm going to compute an integral 2 different ways. One using Greens theorem and one not using Greens theorem. And we'll see that they come out to be the same. So here is my path. I'm going to go from the origin out to 1, 1, up to 0, 2. So this triangle is my path, and we're traveling this in a counterclockwise direction. And my integrand, let's see, I'm going to compute path integral over C of x, y, dx plus y squared dy. So that's the direction I'm going. And I think that that is the whole thing. Okay, so in the absence of Greens theorem, all we can do is parameterize. So I have 3 curves here. First of all, this is in fact a piecewise smooth simple closed curve. Yes? each piece, there are 3 pieces, each one of those is smooth. I have these places where the boundary is not smooth because I've got corners, but the boundary doesn't have to be smooth, it only has to be piecewise smooth, and we've got that. It's a simple closed curve, it doesn't cross over itself except that it begins and ends at the same point. And my P and my Q are continuous. Okay, so Greens theorem does apply, and we'll do it in a minute. But first we're going to do this parameterization. So for part 1 here, this is just the line y equals x. So dy equals dx. And I'll get, oh, and this is on the closed interval 0 to 1. So from 0 to 1, I have y equal to x, so I'll have x squared dx plus y squared, which is also x squared, so I'll get 2x squared dx, which looks like 2/3 x cubed from 0 to 1, or just 2/3. On the second boundary piece, this is the line y equals 2 minus x. So dy is minus dx for x going from 1 to 0. So that's the order I have to integrate that. We have integral from 1 to 0 of let's see, x times 2 minus x times negative, or excuse me, times dx. It's a very difficult angle to write at. And then plus a y squared dy, so y is 2 minus x, so it'll be plus 2 minus x squared, but dy is minus dx, so that's why I have that minus sign there. All right, so what is this? That 2x becomes an x squared, that minus x squared becomes a minus 1/3 x cubed, and then we get a minus 2 minus x cubed 1/3. If I take the derivative of that, the 3 comes down and cancels. I get a 2 minus x squared, which is great. And I also get a minus sign from inside, which would cancel that one. But I'm supposed to have a minus sign at the end, so I better make that a plus. And that is from 1 to 0. At 0, we have, what is that, 8/3. And at 1, we have 1 minus 1/3, that's 2/3, plus 1/3, so 3/3. So 8/3 minus 1, which is 5/3. I'm going to put a little blue box around that so I don't lose it. I'll grab this one also. Whew. And then finally we have boundary 3. And part 3 here, let's see, this looks like x equals 0. We'll take y equal to y. Y going from 2 down to 0. So we travel down the y-axis there. So dx is going to be 0 here. And dy is just dy, it is itself. So we'll have integral as y goes from 2 to 0. xy dx is nothing. Y squared is y squared. And dy is dy. So this becomes a 1/3 y cubed from 2 to 0, which looks like 0 minus 8/3. So we take them all together. We get path integral over c of xy dx plus y squared dy looks like 2/3 plus 5/3 minus 8/3, which is minus 1/3. Okay. So this is the one we want to remember. And now what I want to do is compare that to Greens theorem. So that was fun, right? We got to do 3 parameterized curves. They're lines, but still. We got to parameterize 3 things and compute 3 separate path integrals. Now we can try Greens theorem. Greens theorem says the path integral over c of xy dx plus y squared dy Since C is a piecewise smooth, simple closed curve, and my P and my Q have continuous partials, that we get to use Greens theorem. Oh, and my curve is positively oriented, of course. All right. So that says I'm going to compute the double integral over the triangle, the region R inside my curve, of, all right, I have to identify P and Q. So it's P dx plus Q dy. So I will compute Q sub x minus P sub y dA. And so that will be, well, now I just look. I have x going from 0 to 1. Whoa. 0 to 1. Y will go from x up to 2 minus x. Right, those are my lines. Y equals x. And y equals 2 minus x. And my integrand is just negative x dy dx, which is negative integral from 0 to 1. X dy just integrates to xy. Y equals x. So y equals 2 minus x dx, which is the integral from 0 to 1 of x times 2 minus x minus x squared dx. So I see this 2x, which integrates to an x squared, and I see a minus x squared and another minus x squared. So that's minus 2x squared, which integrates to a minus 2/3 x cubed from 0 to 1, which gives me 1 minus 2/3. And I see that I get 1/3, which reminds me that I had this minus sign here that I should have carried along with me. And I come out with minus 1/3, which is exactly the same thing we got by doing it the hard way. So don't do it the hard way. If you can use Greens theorem, use Greens theorem. It will be the case sometimes that you can't use Greens theorem and you have to parameterize, and that's just the way it is. But when you can use Greens theorem, it's a powerful and really useful tool. The natural question to ask here is, why should this be true? So let's see what we can figure out. So here's the form of Greens theorem. Here's the idea. So I'm trying to compute this path integral, and it's hard maybe. Maybe I have to parameterize 3 separate curves or 15 separate curves. But for whatever reason, I don't want to do this. So the idea is I'm going to take a step backwards. I'm going to start by taking derivatives on P and Q, which seems like the wrong thing to do, right? We're going farther away from our goal. But then I'll replace my single integral with a double integral. So that very broad description, I hope makes some amount of sense, right? If I want to do a single integral, I could first take a derivative and then do a double integral. And one of those integrals would undo the derivative I took, and the other one would give me the result I actually wanted. But the advantage is this may be easier to do. For whatever reason, maybe when you take these partials, the integrand becomes very, very simple like it did last time. Or maybe this region is easier to describe than the path, which also happened last time. Or it may be something like when you do integration by parts, where you choose the parts just right so that what you end up with is easier than what you started with, even though it's equal to what you started with. Right? You're just rearranging things a little bit. So for whatever reason, it may be that this is an easier integral to do. But the idea is you're taking this step backwards first in the hope of making that happen. Now we're going to prove Greens theorem. And our first step is to assume that D is both type 1 and type 2. So it lies between 2 functions of x, and it lies between 2 functions of y. So D is a pretty decent region. Let's say D for decent. I'm just going to draw it as kind of an oval here because that's the easiest type 1 and type 2 region I can think of. say we have points A and B here. And in between A and B, on the top we have y equals g2 of x, and on the bottom y equals g1 of x. So those are the two functions between which the region lies, the two functions that make this a type 1 region. That's also type 2, but I'm only going to deal with the type 1 part right now. And I want to focus on the p part here. So the double integral over d of minus p sub y dA is equal to, well, it's going to be the integral from a to b of the integral from g1 of x to g2 of x of minus p sub y dy dx. And you can see why I've chosen to focus on the part I have. Inside my blue parentheses here, I'm integrating this derivative of p with respect to y with respect to y. I'm just going to undo my derivative. So this is the integral from a to b of negative, I'll put the minus sign out in front, p of, well, p is a function of two variables, so this is p of x comma y, but y is g2 of x, minus p of x comma g1 of x dx. Okay, so that's what it looks like when I perform that first integral. On the other hand, if I go over to the other side and just look at the p part of it, I have integral over c, path integral over c of p dx. Oh, what does that look like? Yeah, I'm gonna draw this just slightly differently to emphasize something. Okay, it could look like that, right? This might not just be a single point, there might actually be an edge there, but it has to be a vertical edge because I'm between two functions of x, so I can't go wandering around. All right, so this would be the integral from a to b. I'm just going to parameterize, go around here. All right, I've got part 1, part 2, part 3, part 4. So part 1, x goes from a to b, and p is p of x comma, well, what's y equal to? Well, I'm on my bottom boundary, so y is equal to g1 of x. dx is dx, because x is my variable. And then I have boundary part 2. And remember, I'm only doing the dx part of this integral. So I'll have the integral from b to b. X will go from b to b. This will be g of, well, x is just b, and y is whatever it is. But dx is 0, right? My x isn't changing. And then I've got part 3, in which x ranges from b back to a. And here, p is evaluated at x comma y, but y on that top boundary is g2 of x. See it? X is the variable, so dx is just itself. That is boundary 3. And on boundary 4, x ranges from a to a, because I'm just dropping down that vertical there. So this is p of a, comma, whatever y is. And again, times 0. My dx is 0 because x isn't changing. So the point here is, oh, this is part 4. Parts 2 and 4 just go away. Part 3, if I want to change that to be integral from a to b, I just introduce a minus sign. So this would be minus the integral from a to b of p of x comma g2 of x minus p of x comma g1 of x. I'm doing a minus there because I have this minus out in front. It's really plus that integral, but that's what I have down here as well. Dx. And if you look at this carefully, you'll see that it is exactly the same as what we found for the p part of the double integral. That's amazing! Now what's cool is because d is also type 2, I could apply this argument equally to, say, x equals h1 of y and h2 of y as my boundaries. And if I go through the argument, everything will work out just like it did here, and we'll find that the q parts match up. The difference, the reason we get a minus sign here, has to do with the orientation and the fact that we're traveling backwards on the top part. But that is, we're traveling from right to left. We're traveling in the negative x direction on the top part. If we do this as a type 2 region, then on the top part, the larger y part, we're actually traveling in the positive direction this time. The increasing y direction. So that's why there's a difference in sign there. It just has to do with the orientation. But all the other pieces work out exactly the same and for exactly the same reasons. Right? I would be integrating here a q sub x, but I'll integrate with respect to x first, and so that will just turn into a q, and I'll have q's in here. And then down here I would be doing q dy, and everything would work out in a very similar way. So I'm not going to go through the second half of the proof, but it works just like this. All right, now this isn't quite complete, because we assumed that d was both type 1 and type 2. What if it's not? Well, it turns out that's okay. We can deal with that. Let's see how. I'm going to make a region here that is not type 1 and type 2. Okay, in fact, that one, let me be a little bit more dramatic here. There we go. This one is neither type 1 nor type 2. Doesn't fit either of those types. But I can subdivide it into regions that are. So I'm going to do that here. Let's see here. Here's, if I start here, come all the way to here, there's a function of x. And, oh, how high up here can I go? Come to here. The trouble is just making this up on the spot. Okay, here's a function of y. It's kind of an ugly function, but it's a function of x. It's kind of an ugly function of x, but it's a function of x. So this region is type 1, but it's not type 2. Because if I look at it this way, I've got this hump in the middle. So I have to divide again. So I have to turn my head sideways and look stuff like this. If I divide like that. So now here is a function of x, here's a function of x, and and this direction, here's a function of y, and here's another function of y. This region lies between curves that are functions of x and between curves that are functions of y. So it is type 1 and type 2. And so is this one. And up top here, but the point is I can subdivide a region that is not type 1 or type 2 into subregions that are both type 1 and type 2. And now look what happens here. Okay. I'm going to call this C1. Here's C2. There's C3. C4, boy, I've made this complicated, I'm sorry. C5, right there. C6. Oh, let's just make this one nicer. C6 will come all the way down there, it'll be fine. And I'm going to get rid of that. I'm going to simplify this a little bit. C4, C5. Okay. And then I've got these red lines in the middle here also. So let me call this D1, D2, and D3. So maybe I haven't drawn that quite right so that all the regions are type 1 and type 2, but the thing I'm about to do doesn't depend on that. Okay, here's the point. If I look at C1 plus D1 plus D2, that is a piecewise smooth, simple closed curve, and as long as P and Q is positively oriented, I need to keep track of my orientation here. And as long as P and Q are continuous, Greens theorem applies, and so I can make this double integral over, oh gosh, let me call this interior E1, here's E2, E3, and E4 on the insides there. Those are the regions. So this would be double integral over E1 of Q sub x minus P sub y dA. And down here, if I do path integral, oh, and I should point out, if I'm doing this positively oriented path integral here, I have to go up D1 and left on D2. All right, now if I do the E2 region, I will have path integral over, let's see, I've got C2, and then I'm going to go down D1. This will be C2 minus D1, P dx plus Q dy, and that's equal to the double integral over E2 of Q sub x minus P sub y dA. And I will have, let's see, on the E3 part, I will have integral of C3, and then I'm going to go, to be a counterclockwise orientation, I have to go down D3, so I'm going to call that a minus D3. P dx plus Q dy equals double integral over E3 of Q sub x minus, I don't want the equal sign there actually, Q sub x minus P sub y dA. And finally on E4, I have my path integral over, let's see now, I'm going to go C5, I'm going to go minus D2, because I'm going in the opposite direction from the one I did before, minus D2. I'm going to go up D3, so plus D3 of P dx plus Q dy. And that will be equal to, according to Greens theorem, the double integral over the region E4 of Q sub x minus P sub y dA. And here's the thing. Since each pair of these are equal, if I add up all the left-hand sides, that will equal the sum of the right-hand sides. So I'm not adding these two things. I'm adding up the dA parts, and I'm adding up the path integral parts, and I'm saying that those are equal to each other. So I only have the one equal sign. This plus this plus this plus this equals this plus this plus this plus this. All right, well what do I get if I add this together? Well, look at this. Remember how this works, right? The path integral of C1 plus D1 is the path integral over C1 plus the path integral over D1. And the path integral over D1 is exactly the negative of the path integral over negative D1. So what I end up with is a cancellation here between the D1 and the minus D1 parts. Those two path integrals will give me the exact same number, but with opposite sign. So they cancel. And likewise, I have a plus D2 here, and a minus D2 there. And a plus D3 here, and a minus D3 there. So what happens is, because I traverse each one of these little red paths in both directions, the two directions cancel out, and it's like I did neither one of them. And so I just end up with the path integral over C1 plus C2 plus C3 plus, why is that C5? Oh, I see. I got rid of that and never adjusted my labeling. That should be a C4. Don't let that part confuse you. That's just a labeling error. So path integral over C1 plus C2 plus C3 plus C4, well, that's the whole curve C. So the right-hand side, excuse me, the left-hand side is the path integral over C of P dx plus Q dy, because it's the same P and Q for each one of those pieces. And the right-hand side is the double integral over, let's see here, E1 plus E2 plus E3 plus E4. Oh, look at that. It's the entire interior, which I'll just call D of Q sub x minus P sub y dA. So again, the right-hand sides, the integrands are all the same. They're all the same Q sub x minus P sub y. There's Greens theorem right there. So Greens theorem, so what this says is, yeah, my first assumption was that my regions were both type 1 and type 2, but in fact they don't have to be, because I can subdivide them into smaller regions that are type 1 and type 2, and then compute my pieces this way, and the extra little divisions I made in the middle just cancel out. And so I end up with Greens theorem anyway. Cool. So that's the proof of Greens theorem. All right, I have some notes here. Some observations that I want to make about Greens theorem. First of all, if F equal PQ happens to be conservative, then the path integral over C of P dx plus Q dy is equal to the double integral over D of Q sub x minus P sub y dA. But remember, for a conservative function, Q sub x equals P sub y. So that's just going to be 0. So if F happens to be a conservative vector field, if your PQ happens, if the P and the Q happen to make up a conservative vector field, then the path integral around a piecewise smooth simple closed curve is going to be 0. We also get a converse here. If Q sub x equals P sub y throughout the region D, so here's my region D, then say I take a couple of points inside of D. Ooh, that's terrible. Let's go with blue, how about? If I take a couple of points inside of D, and I join them by this path C1, and also this path C2, then what I find is that integral around, I want to do a positive orientation, so I'm going to go C2 minus C1. So I go C2 minus C1 of P dx plus Q dy is guaranteed to be 0. Which means that the path integral over C2 of, I'm just going to write this as f dot dr, is equal to the path integral over C1 of f dot dr. That is, for any 2 points in here, any 2 points I choose in D, the path integral between them is independent of path. I will get the same result no matter what path I take. And we already know that that means f is conservative. Okay, that's awesome. So we had that theorem. Says that if f's conservative, then Q sub x minus P sub y is 0, and that was a partial test for conservatism. And then we got this full test for conservatism, which was if Q sub x equals P sub y throughout the region D, and D is simply connected, so it doesn't have any holes in it, then f will be conservative. This is why we need the simple connectedness. Because if we have something like this, where there's a hole in the middle, and that's my region D, then if I take a path on one side of the hole and a path on the other side of the hole, okay, I'm not going to get, excuse me, I'm not guaranteed to get the same result both times. And the reason for that is this. The Greens theorem says my double integral over d of q sub x minus p sub y dA is equal to this path integral. But here's the thing. This path integral, this c, is the boundary of d. Right? D is precisely the region enclosed by c. If I look at my blue curve here, the region D, not the full region D, but the region D I'm using in the theorem, which is the inside of the blue curve, is not everything inside the blue curve. The boundary of that region would actually include the boundary of the hole here. Right? So when I'm integrating over my two curves there, I'm not actually integrating over the boundary of the entire boundary of the region that's enclosed by that curve. Because I've got this hole in the middle here that is not included in that calculation. So we have to have that hypothesis of being simply connected. Second observation, second note, Greens theorem, I already said this, is a generalization of the fundamental theorem of calculus. Because what it says is, to figure out what's happening when you integrate over a region, all you really have to look at is what happens when you look at some kind of antiderivative sort of function on the boundary. The third observation, the third note, is sometimes the path integral is easier, sometimes the double integral is easier. You have to choose one. When you have a choice, you want to choose the one that will get you through the problem faster, right? That will help you solve the problem in the most efficient way. All right, let's try another example. I think we need to do some more examples here. Let's see what we've got going on. One thing is, to use Greens theorem, we will see that we don't actually have to have a simply connected region for that. That it's okay to have a hole in the middle, as long as I keep in mind that the boundary around the hole is part of the boundary of the region, because it separates the inside of the region from the outside of the region. But we'll deal with that a little later. That's just something to point out. Okay, here's our example. I want to do path integral over this path. Let me do the blue. Over this path. My radii are, let's see, 1 and 2. And my integral is integral over c of xy dx plus x cubed dy. All right, we have a choice to make. We can parameterize and do this directly, or we can try to use Greens theorem. Now, if we want to parameterize and do it directly, we'll have to observe that there are 1, 2, 3, 4 boundary pieces, so we would have to do 4 separate path integrals. And right there, that's enough to tell me I don't want to do it. I would much rather try Greens theorem. So I check. Do I have a positive orientation? Well, yeah, that's the intention here, what this little circle means. Do I have a piecewise smooth simple closed curve? Yes, I do. And are my p and my q, do my p and my q have continuous partials? They're polynomials, so yes, they do. So I can do Greens theorem. This will be, by the way, you should pause and work through this yourself if you haven't already. Okay, this should be the double integral over the region enclosed here, d of, I have to identify my p and my q, q sub x minus p sub y dA. And now I'm doing a double integral. So as always with a double integral, I have to choose a coordinate system. This looks to me like a natural coordinate system for polar, natural problem to use polar coordinates in. These are intended to be semicircles, in case that wasn't clear. So I see that I have theta going from minus pi over 2 up to pi over 2. And I have r going from 1 out to 2. I have a 3x squared, so that's r squared cosine squared theta minus x, r cosine theta, times dA, which is r d theta. And I will let you work through the actual calculation of that. All I want to do right now is get it set up and show you that this is going to be a much nicer integral to do than parameterizing 4 separate arcs on that boundary curve. The cosine squared requires a trig identity. Cosine squared theta is equal to 1 plus cosine 2 theta all over 2. So you can use that identity and do the rest of the problem. Okay, I'm going to do the same path integral, x, y, dx plus x cubed dy. This time I want my region of integration to be the region between these two circles. Ooh, circles, those are circles. So it's like this one, except instead of just cutting it in half, I'm going to take the whole region, the whole annulus between the two circles. So I'll do the shaded part here. Shade, 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 shade. What you'll notice about that is that it is not simply connected. There's a hole in the middle. So here's how I'm going to handle that. I'm going to start back here. Let's say green. I'm going to start back here, travel around to here, come into the middle, travel around the inner circle. Now I have to be careful here. When I travel around that inner circle, I still need a positive orientation. Before we said positive orientation means counterclockwise, and here I've drawn this clockwise. But remember, there is that parenthetical observation. Really, positive orientation means that the region bounded by my curve should be on the left. So as I walk around this, I need the shaded part on the left. So this is the positive orientation on the inside here. And then I come back out. And then I continue around to where I started. And what you'll notice is that the little part that connects the two circles was traversed in both directions. So it's going to cancel out like it did when we subdivided our regions before that weren't type 1 or type 2. So I don't actually need that part. I need the positive orientation on the outer circle and the negative orientation on the inner circle if it were just a circle by itself, right? As opposed to thinking of it as the boundary of my region here. But I can still use Greens theorem as the point of that. So here we go. This will be double integral. It's the same thing here, 3x squared minus x dA over the region bounded by those two curves. And this will be, let's see, now I have theta going from 0 to 2 pi, r from 1 to 2, and again it's going to be 3 r squared cosine squared theta minus r cosine theta times r d theta. R d theta. And again, I will let you work through that actual integral. I'm just interested in setting it up for right now. There's one more thing I want to talk about. We'll do some more examples in class together, but there's one more thing I want to talk about in this section. And that is the area formulas. These are really neat, and we may have a project where you have to use them. So if I want to find the area of the region D, I can compute that by finding the double integral over D of 1 dA, right? Greens theorem says if I can come up with a P and a Q so that Q sub x minus P sub y equals 1, then I can also compute this as a path integral around the boundary of D, which, by the way, has a notation. It's kind of backwards 6-ish sort of thing. In front of the D, that means the boundary of D. So you'll see that from time to time. So I have to come up with the P and the Q to make this work. Well, look, I need Q sub x minus P sub y equal to 1. The easiest thing to do would just be to let Q equal x and P equal 0. So take P equals 0, Q equal x, then this double integral for area becomes a path integral of P dx, 0, plus Q dy. And that's it. There's a really nice formula for my area. Alternatively, we could do P equals minus Y and Q equals 0. So if P is minus Y, then Q sub, and Q is 0, then Q sub X is 0, P sub Y is minus 1, so minus P sub Y is 1. And over here we get P dx plus Q 0 dy. And I have the minus sign in front here. Or, another option, we could take P equal to minus 1/2 Y and Q equal to 1/2 X. Then Q sub X is 1/2, P sub Y is minus 1/2, so 1/2 minus minus 1/2 is also 1. So this would be path integral over C of 1/2, and we'll have X dy minus Y dx. Would be one way to write that. Or anything, you can choose any P and Q you want as long as Q sub X minus P sub Y comes out to be 1, because we know that that gives us the area. So this is really neat. Okay, here's what it says. It says, if you can walk around the boundary and compute this as you go, you can find the area, which seems really counterintuitive, really strange, right? Because it says, basically, walk the perimeter and you will know the area. And there are actually things that have been manufactured called planimeters that you can roll along the ground, around, traveling around a field or a lake or something, and it will compute the area of the lake for you. How awesome is that? That's really cool. Okay, so I'm not going to do an example of that right now. We may do one in class. There will be some in the web work. This is one of those things that you just want to know. Okay. X dy, I think that's the simplest of the three formulas. All three are in the book. That's why I showed all three here. But typically, you're just going to pick one and do it. Okay, so that's Greens theorem. We're going to do more of this in class. It is a major theorem in this course and in all of mathematics. It's one of the really big theorems. And it's a theorem that you will encounter in other classes like physics. So that's it for now. I will see you in class.